All right, here's the chapter 17, conceptual question solutions. Again, I would much rather have done this in class, but apparently we don't do that. So, I mean, there was only a half inch of snow today, for crying out loud. Just drive carefully, for crying out loud. Too much crying, too much out loud crying. Anyhow, this is asking what, basically to look at what happens to light waves as they go into another substance here. So we know that the frequency has to stay the same because the frequency is caused by what makes the light waves. It's how many waves per second are produced. So whether you go into a substance, one substance, or not, or you stay in the same substance, the frequency can't change. So here we've got a wavelength, and I initially screwed up my calculation of this, but basically what I'm looking at here is, in fact, this isn't 4, which is the wavelength. That is going to be 2. And I need to change that color. Yeah, there you go. Because I just didn't even look. I don't know why I thought these were closer together. But these things are 2 apart from each other. This looks like the wavelength is 6 because it's 3 units from crest to trough, so it would be 6 from crest to crest. So essentially, the original wavelength over the new wavelength, it's bigger in a vacuum. That means that the speed is bigger in a vacuum using the general wave equation. So I get 6 over 2, and that means my index of refraction is 3. So it kind of explains that here. Here, the index of refraction is 2, and again, I screwed up how I tried to draw this. So I think it's okay. So 3 units for the new wavelength. So just like how this was 3 from crest to trough, there should be 3 from crest to crest. Down here, it says this figure shows a double slit experiment for questions A through C. Will the fringe spacing increase, decrease, stay the same? So here's my general formula for diffraction. And these are dark, bright, dark, bright, dark. So constructive interference, destructive, constructive, destructive, constructive, destructive. So if the distance to the screen is increased, basically what that means is nothing about this is changing, so the angle is going to be the same. Well, if you've got a longer distance but the same angle, these fringes will get further apart. Here, if the spacing between the slits is increased, that means this increases. Therefore, if we've got the same color of light, looking at the same particular order number, which I've described in an earlier ed puzzle, then if this right side of the equation stays the same and d increases, then this sine theta has to decrease. So the bands would get closer together. The fringes would get closer together. So if the wavelength is increased, again, for a given order number and for the same spacing for the slits, if the right side of the equation increases, the left side would have to increase. So longer wavelength means bigger angle. So the spacing between the fringes would increase. On the back, we had a decent discussion about this in my B cohort. I haven't seen my A cohort. It'll be 3 weeks, practically, where I have seen you maybe once. So we just haven't gotten there. Again, hopefully the ed puzzles have helped. That's why it was important to do those. So we've got a ray of light coming in. If you're hitting this dense substance, you would have a phase shift. It would flip. If you are going through this dense substance and then hitting a more moderate substance of lower optical density than what you're coming from, and 1.33 is lower than 1.4, we would have no flip occurring. So I see flip, no flip. So that's a yes and that's a no. If this thickness, do the 2 waves reflect, and if you're constructively, destructively in between. So it's saying the thickness is half a wavelength. So this is 1/2 of a wavelength. So, ooh, I think I screwed up with this. I'll have to look at it. So it's asking, do the waves interfere constructively, destructively, or in between? So if the thickness is a 1/2 wavelength, then since I'm going down and back, the total path difference is 1 full wavelength. So that would still be destructive. Okay, so I did do that right. Hey, that's good to know. For this one, similar type of problem. Here we're going from 1 to 1.2 to 1.5. So here, both these interfaces, we have a flip or a phase shift. So that is a yes and a yes. And it says here the thickness is also 1/2 a wavelength. So the thickness between here and here, 1/2 a wavelength. And unfortunately, I can't draw an arrow with 2 arrows. Oh, maybe I can. Maybe I can. This thickness from here to here, nice, is T over 2, 1/2, or wavelength over 2, 1/2 a wavelength. And I can't make that symbol here. So that means going down and coming back, this part of the wave travels an additional full thickness. So since it travels full thickness and these two would be in phase, they will interfere constructively. So we would see a bright color of light for whatever wavelength we've got. Thanks. Hopefully that helps.